Algebra 2, Target 3. I can solve a system of linear equations and interpret their solutions. This is a couple-day target. Our focus today is going to be solving by graphing. What is a system of linear equations? Quite simply, a system of linear equations is just two or more equations or two or more linear equations. Usually we just start with two linear equations. All right? And the solution to a linear system is any point that works in both equations. And we can look at it a couple ways. We can look at it symbolically, or you can look at it graphically. If you look at it graphically, the point that works in both lines is the point where the two lines cross. All right? So here's an example of a linear system that's been worked out. What they did, they graphed it. So they took each equation right here, solved for y, and plotted the graphs. And they saw that the graphs crossed at the point 3, -1. Now, anytime you're doing things graphically, as humans, we can kind of maybe, our points can be off, our lines may not have the correct slope we intended. So we need to be sure of our solutions. And we be sure of our solutions by checking them. And we check them by putting them back into the two equations. You need to make sure you check both equations, because the point must work in both equations. If it works in one, that's great, but not good enough. It needs to work in both. So we check our point in the two equations and make sure we get a true statement. Check the point in the first equation. We got a true statement, 8 equals 8. Second equation, 18 equals 18. That is the solution to this system. Right? Most of the times you're going to find one solution, but not always. There's 3 different situations that could arise. Right? You could come up with one solution. This is called a consistent and independent system. We call it consistent because there's a solution, and we call it independent because we got 2 different lines that are finding that solution. We got one solution for those 2 lines. You could also, in the second figure here, you could come up with infinite solutions. Basically, it looks like there's one line, but no, the 2 lines that we graphed lie on top of each other. They're basically the same, 2 different forms of the same line. This is called consistent and dependent. Consistent because we found solutions, and dependent because there's so many of them. And then the third situation we have is you got 2 lines that never cross, parallel lines. This is called an inconsistent system because there's no solutions. Nothing works in both lines. You might find something that works in one, but not the other. All right, so let's work through this example. We got an example. Solve the system, classify it as consistent and independent, consistent, dependent, or inconsistent. Let's start by graphing it. All right, so we got 2x plus 5y equals 6. All right, we'll solve for y. I'm going to subtract 2x from both sides. I got 5y equals -2x plus 6. We'll divide by 5. Y equals -2/5 x plus 6/5. All right, let's take a look and graph that right now. 6/5 is about 1.2. Our slope, it's -2/5, so we'll go down about 2 from there and over 5. Connect and extend. All right. Let's graph the other one in red. 4x plus 10y equals 12. We'll subtract 4x. So 10y equals -4x plus 12. Divide by 10. So y equals -4/10 x plus 12/10. All right, 12/10, that's about 1.2. Plot it right there. Our slope is -4 over 10. Plot it right there. Connect and extend. All right, notice those 2 lines appear to be on top of each other. Well, we would call that our consistent dependent system because we got infinite solutions. Those lines cross everywhere. Now, I didn't simplify the fraction on here right away. I usually do. But I didn't because I didn't want you to see it right away. But if we did simplify those, what would we get? Well, -2/5 x plus 6/5. And what do you notice about those 2 equations then? A consistent dependent system, basically, you got the same 2 equations. and there's infinite solutions. They're always going to work because they're the same thing. All right, let's look at this one. 3x minus 2y equals 10, and 3x minus 2y equals 2. Let's graph these. We'll start with 3x minus 2y equals 10. We'll subtract 3x. Negative 2y equals negative 3x plus 10. Divide by negative 2. Y equals 3 halves x minus 5. All right, we'll graph that. Negative 5, 1, 2, 3, 4, 5. Then up 3 over 2. Let's do the next one in a different color. We'll do red. 3x minus 2y equals 2. We'll solve that again. Subtract 3x. Negative 2y equals negative 3x plus 2. Divide by negative 2. Y equals 3 halves x minus 1. Our y-intercept is negative 1. Up 3 over 2. Connect and extend. All right, those two lines never cross. We got ourselves an inconsistent system. A couple things that should key us off to this fact that this is an inconsistent system is, first off, 3 halves x, they both have the same slope. Second off, right from the get-go, we got 3x minus 2y equals 10, yet at the same time, 3x minus 2y equals 2. How can the same thing be equal to two different things? Well, it can't. That's why it's called inconsistent. You cannot have the same thing equal to two different things. All right, let's look at one more example. We got negative 2x plus y equals 5 and y equals negative x plus 2. Let's graph those. I'm going to graph the bottom one first because that's easier to graph because it's already in y equals form. Negative x plus 2 will go up 2, and then our slope is down 1 over 1. Connect and extend. And then we'll graph the second one in blue. Now, I said the other one was easier. This one's not hard. Just because the other one's easier doesn't mean this one's hard. We'll add 2x. Y equals 2x plus 5, a y-intercept of 5. Down 2 over, or up 2 over 1, connect and extend. And it appears that these two lines cross at the point negative 1, 3. All right, and I say it appears because I may have done everything right, but my hand slipped, my ruler has a bump in it, and I may not get my slope correct, and the line is off a little bit, or something like that. Right? So what we need to do is we need to check. And we check by plugging our points back into the equations. And you must do both, because there may be a point that works in one but not the other. So we need to check to make sure it works in both. We'll check the green one first. I'll plug in my point, negative 1, 3, so that gives me 3 equals negative 1 plus 2. And yes, 3 equals 3. That works. Now we'll check the blue one, negative 2x plus y equals 5. We'll plug in our point, negative 1, 3. So negative 2 times negative 1 plus 3 equals 5. Negative 2 times negative 1, 2 plus 3. So 5 equals 5. We check them both off, and we're happy because we have found a solution. All right. In conclusion, a system of equations is two or more equations. And the solution, graphically, is where those lines cross. You're going to graph them, see where they cross, and then verify your solutions by plugging them into the equation and simplifying to see if that worked out.